Okay. So the first speaker of this session is Zhu-Xi Luo, and she's going to be talking about Moire magnetism in van der Waals heterostructures. Okay.
Okay, thanks for the introduction. Hello, everyone. Welcome to my talk on Moire magnetism. So this talk is based on the following collaborations with Khazra Hijazi and Leon Balint. I will mainly focus on the continuum field theory description of heterostructures of two-dimensional magnetic materials and their implications. By magnetic materials, I mean intrinsic magnetism, not spontaneous magnetism. To gain some intuition, let's start by considering a single layer of honeycomb lattice with antiferromagnetic nearest neighbor Heisenberg interaction. Since honeycomb is a bipartite lattice, it's easy to see that the system will have Néel order, namely the spins in one sublattice pointing in one direction while the spins in the other sublattice pointing in the opposite direction. The order parameter will be the Néel vector n. Now, what if we add another identical layer but twist it by a relative angle? One observe that there is this superlattice structure of this bilayer system. Suppose there is an antiferromagnetic interlayer interaction that is also of Heisenberg form. Then near this AA stacking regions where the red sublattice of one layer is on top of the red sublattice of the other layer, and also blue on top of blue, then because of this antiferromagnetic interlayer interaction, the Néel vector from the two layers will point in opposite directions like this. Near the AB stacking regions where the red sublattice in one layer is stacked on top of the blue sublattice in the other layer, then by comparison, the Néel vectors from the two layers will point in the same direction. The main message is this: since different regions of the system favor different configurations, we have generated frustration. Basically, the Néel vectors must rotate between the different regions. We can also use ferromagnetic interlayer interactions and get a similar prediction. Now, let me spend one slide motivating the work. I think I don't need to motivate the Moire part too much, but let me say something about the magnetism part, as most of the studies of the Moire systems focus on the electronic properties. So what we have in mind are the van der Waals magnets, which are two-dimensional atomic crystals exhibiting intrinsic magnetic properties. So one of the theoretical motivations to study such materials is that they have been found to realize the fundamental spin Hamiltonians, such as the Heisenberg model, Ising model, XY models, etc. So therefore, these materials provide a platform to thoroughly examine various well-established theories. And they also allow for the control and the manipulation of magnetic states through coupling to external perturbations, such as strain, light, gating, proximity effect, and Moire patterns. And there is also device applications due to the tunability and flexibility of such materials. And there are really a lot of them. This exciting zoo of materials contain insulators, semiconductors, metals, ferromagnets, antiferromagnets, etc. So the possible models are numerous. In addition, as we have seen in the previous slides, one will have frustration due to the Moire patterns of various stacking, which would further lead to a lot of interesting physics. And our main tool will be the continuum theory. Continuum theory is simple because it relieves the pressure to study a huge number of sides and spins with complicated local environments due to stacking. And also it can restore periodicity in a generically only quasi-periodic system. Furthermore, it combines the two-dimensionless parameters, the ratio of interlayer to interlayer hopping, and the twisting angle to a single one. And the derivation of our continuum model is inspired by the Bitstreiter and McDonald model for twisted bilayer graphene, but our derivations will be in real space. We construct the model based on the following two assumptions. So the interlayer exchange should be small compared with the intralayer exchange, such that, and that the twisting angle is small. We can also treat general elastic deformations, but I will focus on the twisting case in this talk. And these assumptions are widely applicable and achievable in van der Waals systems. And under these assumptions, the interlayer coupling and the displacements have significant effects only at low energies or long range. The first twisted bilayer system we will consider is, as mentioned previously, that of the twisted bilayer Heisenberg antiferromagnets on honeycomb lattices. We have the Néel ordering on both lattices. So here, the subscript L is the layer index, and there's a single ion anisotropy, which is present, for example, in the material manganese phosphate. The interlayer coupling can be described by the minimal Fourier expansion based on the Moire translation symmetries. And these small q's are the Moire reciprocal lattice vectors. We can see that this is basically a coupled nonlinear sigma model with spatially modulating coupling. So one can further rewrite the Hamiltonian in terms of dimensionless parameters where the Moire scale is of order 1. We observe that the interlayer term is indeed ferromagnetic or antiferromagnetic depending on the sign of this phi function, as we expected from the previous slides. Therefore, when this alpha term is large, the neo vectors tend to twist in different domains of phi of x. So we have studied this Hamiltonian using perturbation, strong coupling, dimensional analysis, and numerically solving the equation of motion. So the phase diagram is shown below. But there are two such twisted phases with Moire periods, but with different symmetries. These states are no longer collinear as that in a single layer, but in general coplanar. There's still a collinear region in the phase diagram when beta is large, when beta is dominant, as the single ion anisotropy when d is larger than 0 favors all neo vectors to point along the plus minus z directions. One can also compute the Magnon bands, which interestingly flatten at large alpha. Well, this is due to the fact that the Moire potential term become alternated deep Waals and hard Waals, confining the Magnons to either of the two domains. Of course, one can further study various models using this formalism. For example, one can generalize to the case of zigzag antiferromagnets, which happen to be the cases for these materials, iron thiophosphate, cobalt thiophosphate, and nickel thiophosphate. It's a collinear magnetic order, which further doubles the unit cell. One can follow the similar procedure to derive the following Hamiltonian. Now the Moire potential contains 3 flavors corresponding to the 3 possible spatial orientations of the zigzag chains of light spins. So at strong coupling, instead of the 2 different domains, as in the case of a nail order, now we can have a tiling of 6 possible zigzag domains, which evokes a dice lattice structure. One may also look at homobilayers of ferromagnets. In particular, this material chromium triiodide, which has a similar structure as the ruthenium trichloride, has an interlayer exchange with a strength and sign depending upon the displacement between the neighboring layers. Incorporating the DFT calculations of the interlayer exchange profile into a continuum model, we obtain the same Hamiltonian as the nail order case, but with a different phi of x. And also the nail vectors n are substituted by the magnetization vector m. Again, the Moire potential can lead to a twisted phase, where there are large regions with a net magnetization of orange color, while other regions have vanishingly small net magnetization of white color. In particular, we were able to identify the magnitude of twisting angles where the transitions to the twisted phases happen, which is promising to be seen in experiments. And next, let me switch to another topic, another subtopic where we take untwisted heterobilayers of ferromagnets together with antiferromagnet to generate skyrmions of Moire scale. So this skyrmions are non-trivial magnetic textures protected by topology defined using this expression. So this is the decoupled layer Hamiltonian we will consider with DM interaction in the ferromagnetic layer and anisotropy in the antiferromagnetic layer. We assume that the spin stiffness for the antiferromagnetic layer is very large, such that the layer is mainly static, and the nail vectors will point along the z direction due to anisotropy. So the effective Hamiltonian for the ferromagnetic layer is just the kinetic term, the DM term, and the Moire potential. This figure depicts the Moire potential, where the modulation comes from, since we no longer have twisting, the modulation just comes from the lattice mismatch between the 2 layers. And here, this small d is the reciprocal lattice vectors of the Moire lattice again. So in this Hamiltonian, the kinetic term favors uniform magnetization. The DM term itself prefers spirals with periods depending on this parameter beta, while the Moire potential again favors a twisted configuration. So there is a competition between the alpha and beta terms, leading to a possible commensurate incommensurate transition. focus on the states commensurate with the Moire potential. We note several different possibilities with different symmetry patterns. In particular, there is this Moire skyrmion phase with one skyrmion per Moire unit cell. We have also obtained the phase diagram numerically using micromagnetic methods, where these commensurate phases form the main body of the phase diagram. We have also studied the commensurate incommensurate transition perturbatively, but we will not further discuss it here. A possible materialization is the MMPS3 for the antiferromagnetic layer and the genus TMD, transition metal dihydrocogenase, for the ferromagnetic layer, which were shown to have DM interactions and can host skyrmions in a monolayer. So there are a lot of promising future directions, including adding external fields to train the phase transitions. Adding fields in the, for example, in the homobilayer antiferromagnets effectively corresponds to training the beta, the anisotropy term. So one can expect to be easier to get to the twisted phases when a field is present. One can also consider other lattices, interactions with charge carriers, and more ambitiously, even heterostructures of topological phases. It's also important to study how to measure this magnetism and its consequences. Okay, so in summary, the take-home message is there are a lot of exciting stuff waiting to be discovered in Moire magnetism. And thank you. I can take questions if there's time.
Yep, there's about 1 minute left. Thank you very much for a very nice talk. So the one question that came in on time is, how do you distinguish nearby domains with different magnetic phases in experiments?
Yeah, that's one of the future directions that I mentioned here. It's especially difficult for the insulating materials, but I suppose maybe one can use direct imaging methods, but it will be an interesting future direction.
Yeah. Okay, so there's one more question in the Q&A. If you look at it and answer it offline, we're going to have to move on to our next speaker. But thank you very much. So the next speaker in this session is Sabayasachi Tiwari, and they're going to talk, if they want to turn on their camera and start sharing their screen.